Alright, week 2 pre-lab video. This video we're going to talk a little bit about a review of examine if closed, examine if open, and output to energize. So we've already talked a little bit about this. And we're going to have a quick review. Examine if closed, otherwise known as examine on, looks like a normally open contact, but do not think of that as normally open. When a PLC processor sees this instruction, it is looking for a closed condition. In other words, is the input device associated with the XIC instruction closed? If it is, the instruction would be true or on. Likewise, if the input device is open, the instruction would be false or off. XIO, examine if open or examine on. Actually, I take that back. That needs to be examine off. Let's change that real quick. Okay. Easy to fix. Examine off. Looks like a normally closed switch. It's not normally closed, it's examine off. When the PLC processor sees this instruction, it's looking for an open condition. In other words, is the input device associated with the XIO instruction open? If it is, then the instruction would be true or on. Likewise, if the input device is closed, the instruction would be false or off. And when we say on or off, we're talking about logical continuity within the program advancing to the next part of the program. The next thing we're going to look at is an output to energize. So what do we want to turn on? This is what it looks like. It looks like similar to a ladder logic diagram with the circle, but this is kind of the little parentheses. And this is the address. So it's output 00 is the address associated with this instruction. Just like this input 00 is the address associated with this instruction. So an output to energize, this is an output instruction, and for it to be true or on, all preceding instructions in the rung must be true. If all preceding instructions are not true, the output device associated with the OTE instruction will be off. Alright, so now we're going to look at electrical continuity versus logical continuity. For a real-world hardwired output to operate properly, you must have electrical continuity. So right now, in this little ladder, rung of the ladder, we have 120 volts on L1, and then we have a neutral. So for this 120 volts to make its way all the way to the light and to form a complete path to illuminate this light, because current's flowing through this line, we have to close this push button. So it's a normally open push button. When we push it, it closes. Now we have electrical continuity through the switch, and we're going to illuminate the light. So for pilot light to turn on in rung 1, you must have electrical continuity between L1 and N, neutral. In other words, when voltage is applied to L1 and the normally open push button is pressed, the red pilot light will come on. When you release the push button, the light will turn off. Pressing the push button provides a path for current to flow, and we have electrical continuity. Now, a PLC program is a little different. A PLC control system is different in that only requires logical continuity to operate. You will not have to have electrical continuity to turn on an output. I know that don't quite make sense, but you can actually use the absence of electrical continuity to turn on an output dependent upon the program. So it looks the same, right? We have a normally open switch and an output. Remember though, this is not normally open. This is examine if closed. So if in this rung, if this is wired to a closed switch, this output's going to be on. If it's wired to an open switch that's not being pressed, the output will not be on. The rung above contains an XIC, examine if closed, instruction, and an OTE, output to energize, instruction. When the processor scans this rung and it comes to the XIC instruction, it checks the status of the input device associated with its assigned address to see if it's closed. If the input device, in this case the normally open push button that we was using earlier on, is closed, the output red pilot light will turn on. If the push button is not closed, the output will remain off. Logic alone is turning the output on or off. If the input in rung 1 is closed, it is said to be true or have a 1 in its status. If it is not closed, it's said to be false or a 0 in the bit status. For an OTE instruction to be true, 1, all preceding instructions must be true. When all instructions in a rung are true, the rung is said to be true. So what that's saying is, if this goes true, it's examine if closed. If this switch that's wired to input 00 is closed, this condition is met, this rung is true, and this output's turned on. Let's scroll down. Well, I don't mess things up. Let's scroll down a little bit and look at another example. This is examine if open and an output. So the same switch, this is a normally open switch wired to this examine if open, and this is an output to energize, the same output. So when the processor scans this rung and it comes to the XIO, examine if open, instruction, and it checks the status of the input device associated with its assigned input address to see if it's open. If the device, in this case the normally open push button we've been using the whole time, is open, the instruction would be true and the red pilot light would turn on. So we would not have electrical continuity because we've got a normally open push button wired to this. But we're going to turn this output on because we have logical continuity. If the push buttons were closed, the instruction would be false. So if you close the push button, providing electrical continuity, then you no longer have a logical continuity to turn on the lamp. If the push button were closed, the instruction would be false, the light would turn off. For this to make any sense at all, you must remember that we are dealing with logical continuity, not electrical continuity. All right, we're going to move on to latch and unlatch. So real-world hardwired latching relays are often used in conjunction with lighting applications. So like this is considered a lighting contactor, is what they're talking about. This is only one of many applications. You can take a latching relay and a normally open momentary push button and send a signal to the coil of the latching relay and cause the contacts associated with the relay to open and close by simply pressing the momentary push button. When you release the push button, the coil is no longer energized, but the contacts stay in their changed state until you unlatch the relay. So you push the push button and you latch a relay, you have to push another push button to unlatch it. So the electricity that's latching that turns that on leaves, but the relay stays latched. You would need another normally open push button to unlatch the relay since it has both a latch and unlatch coil. So two separate coils latching and unlatching a set of contacts. The mechanical linkage causes the relay to remain latched and is also used to unlatch it. Note, a word of caution is needed at this point. A latching relay is retentive. In other words, it remembers what state it was in if the power fails. If it was latched when the power failed, it will be latched when the power is restored. Latching relays and latches in a PLC program can be dangerous. So if the power goes out and the application that this is being used on, the machinery or whatever, quits running, whenever the power is restored, it will start right back up. It'll start right back running because it remembers that it was latched when it was shut down. So right here it's giving you an example of the latching contactor it's talking about. When you press PB1, push button 1, you're latching the contactor. When you press PB2, you're unlatching the contactor. So when you latch the contactor, you turn on the green light, and when you unlatch the contactor, you turn on a red light. When PB1 is pressed, the latch coil will receive a signal, and the green indicator light will turn on. The red indicator light will turn off. Likewise, when PB2 is pressed, the unlatched coil would receive a signal and the green indicator light would turn off. The red indicator light would turn on. When it comes to programming the latch OTL and the unlatch OTU instruction, you will need to keep in mind that these are retentive output instructions. You will also need to keep in mind that an OTL instruction can only turn a bit on and an OTU instruction can only turn a bit off. These two instructions are used in pairs. In other words, they will have the same address. So if you want to turn something on and turn something off, you're going to address them with the same address. So therefore, when you latch it, you can only use an OTL. When you unlatch it, you only use an OTU, and they will have the same address. They are retentive. They remember the last state they were in when the power is restored. Always remember that any equipment associated with them will start back up when the power is restored if they were latched when the power failed. Give a lot of thought to their use in a program. While they are powerful instructions, they can also be deadly. So skipping on, getting away from the latch, and we'll use that latch when we get in the lab again. So just kind of take some notes on it, understand how latch works and how unlatch works. The next thing we're going to talk about is B3. B3 can be thought of as an internal relay. The B3 file table is composed of 256 one-word elements, 0 to 255. Each word consists of 16 bits. So when I say a word element, think of the input and outputs. Whenever I told you the word, what a word was and what a bit was, that's what it's talking about. So if you look at the addressing of B3, you have B3:0/0. This is the word, this is the bit. So for every one of these words, you're going to have 15 bits. And those are all separate internal relays. So this address right here is its own address. You can turn this on and off in the program, and it's specific to this one address in a bit box. This address is a totally different address. It could be, they have the same word, but it's two different bits. So if this was turned on, it has nothing to do with this. So this will go 0/0, 0/1, 0/2, and so on and so on and so on, all the way to 15. That makes 16 bits counting 0. Now, the next word would be B31/0, and then the next bit in that word would be B31/1, B31/2, so on and so forth. And that goes all the way up to 255. So we're showing you 3 bits for 0, the word 0, out of 16 bits. We're showing you 3 bits for the word 1 out of 16 bits. And there's 256 words. So there's a lot of storage capabilities there, right? We have a lot of internal bits that we can use when we're programming a PLC.